I'm going to get started. My name is David Matlack. I work at Google, and I'm going to be talking about message passing workloads in KVM and their performance. So I'll give a brief overview of what message passing workloads are, and then I'll use TCPR to demonstrate what the performance is and where the overheads are. I'll talk a lot about interprocessor interrupts and halts and how those perform in a KVM guest. And this will be pretty x86 specific, so raise your hand if you want me to explain something more. And then at the end, I'll talk about halt polling, which is a feature you can use today to improve the performance of message passing workloads. So message passing workloads, this is not the first time they've been at KVM Forum. But if you haven't heard of them, imagine any workload where you have multiple threads passing messages in between them. And the characteristic of these workloads that we really care about is that they very rapidly switch between running and idle. So they're running when they're receiving a message, processing the message, and then they're idle when they're waiting for the next message. So this is your web servers, your database servers, where they're sitting on an open TCP connection, waiting for a client request. That's when they're idle, and then once they receive a request, they service it and send the reply. That's the running half. But also multi-threaded applications that use condition variables to do wait signals. These also have the same characteristic of quickly switching between running, where they're doing whatever, and then idle, where they're waiting on a condition variable. And good benchmark of message passing workloads is TCPR, which is part of the NetPerf benchmarks, if you haven't heard of it. So the intuition with a lot of these workloads is when you're running a virtual machine and you're not doing any I/O, so maybe you're running your multi-threaded workload with these condition variables, primitives. Well, when there is an I/O involved, then we should run at near native performance. But the reality is these workloads can often be 2 to 3 or more times slower. So loopback memcache, meaning you have your web server and your memcache server running inside the same virtual machine, so you're not going across the network to hit the memcache server. The latency of going to memcache and back is 2 times higher in a KVM virtual machine. And these Windows event objects, which is what in a Windows operating system, what they call their wait signal primitive, the latency of those is 3 to 4 times higher. So we can use loopback TCPR to better understand the virtual overheads of these message passing workloads. Because loopback TCPR, you have a client process and a server process. They maintain an open TCP connection between the two, and then they ping pong 1 byte of data back and forth. So one transaction is starting at the client, sending a byte to the server, and then the server sending 1 byte back. And we care about, well, what is the latency of that one transaction? And it's loopback, so there's no, networking, whether it's networking hardware involved or an emulated network device. So this is the performance of loopback TCPR on an Ivy Bridge machine running KVM in a 3.11 host kernel with some slightly modern KVM with backports. At one CPU, the native and virtual performance are about the same. They both run at about 10 microseconds for each of these transactions. But as you go to 2 and higher, they diverge. They both get worse, but virtual diverges a lot further than the physical performance. So at 2 and higher CPUs, 3x higher latency in a virtual machine, and that's about 25 microseconds for this benchmark. So if you see something slow on one and something slow on more than one CPU, you could probably guess, well, on one CPU, when you're passing messages back and forth between 2 threads, well, you're just context switching between those 2 threads. But if you're message passing between different CPUs, well, you're probably doing some sort of cross-core communication, which maybe is interprocessor interrupts. But what's actually going on under the hood, and how is this being virtualized, and where's the latency? VM exits are a good place to start looking when you're looking at a virtualization overheads, and luckily there's a tool, perf KVM, that most of you probably know, that lets you count and time VM exits. Okay, so I ran TCPR with 1 and 2 CPUs, and then counted the number of VM exits for each, and then correlated it with how many transactions there were. So with one virtual CPU, there is some noise overhead of VM exits, but their per transaction of TCPR is essentially 0. So there's basically no virtualization overhead correlated with each transaction. But at 2 CPUs, you get a little over 9.5, or about 10 MSR write exits and 2 halt exits. So halt is a CPU instruction that you execute when you have nothing to do, and it basically tells the CPU, stop executing instructions until an interrupt arrives. So if our virtual CPU is executing this instruction, that means it's decided there's nothing to do. And we know message passing workloads switch between running and idle, so this isn't a huge surprise. 10 MSR writes. MSRs are model-specific registers. They're basically CPU registers that you access with a special instruction. 8 of the 10 are writes to the APIC timer, which is a per CPU timer that can be used to implement a tick or HR timers. So you write a value to this register, and the timer starts counting down and fires an interrupt when it gets to 0. So this is an artifact of the guest being a no-hertz kernel, and I'll talk more about that later. The other 2 MSR writes are to the interrupt command register, and this is how you send interprocessor interrupts. So, and like we said, this is how you would deliver messages across CPUs. So taking those exits and putting them on how this is flowing for one transaction of TCPR, if you start at the top left, the client sending message to the server is an interprocessor interrupt. The server was halted when the interrupt was delivered, comes out of halt, writes to its APIC timer twice, and then the same thing happens again. The server sends a message back to the client. So the important thing here is that we had 12 total VM exits, but not all of them are on the critical path. So when the client, after it sends its interprocessor interrupt to the server is now, the performance of the transaction is now directly up to how quickly the server runs. Right? So the 2 timer writes that the client does after it sends its interrupt aren't on the critical path. Right, so we started with 8 MSR exits to write to the APIC timer, but only 4 of them are on the critical path. And like we said, this is because of the no-hertz guest kernel. So when you have a no-hertz kernel, every time you switch to the idle process or anytime you switch from the idle process, it reconfigures the scheduler tick. So switching to the idle process will disable the scheduler tick, and switching from the idle process will enable the scheduler tick again. And for this case, the scheduler tick is implemented with the APIC timer. Why are there 2? Well, the first one is always an HR timer cancel, and the second is always an HR timer start. So this is not I'm not completely familiar with how the no-hertz kernel is implemented, but it sounds like this is something that could be merged into one MSR write. But in practice, this adds about 3 to 5 microseconds to the round-trip latency. So, yep. Halt. We talked about halt already, but the interesting thing that we didn't mention is that halt is not on the critical path, meaning executing the halt instruction is not on the critical path. Coming out of halt is. The way halt works in KVM is when a guest executes the halt instruction, it drops out of guest mode and into host mode, where KVM takes over, and KVM places the vCPU thread on a wait queue and then yields the host CPU. So the IPI interprocessor interrupt plus the halted CPU coming out of being halted, that part is on the critical path. And the way that works in KVM is we start at the bottom left where the vCPU1 is going to send an IPI to vCPU0. Writing to the APIC interrupt command register is how you send an interprocessor interrupt. That causes a trap into KVM. KVM emulates the IPI by, in KVM vCPU kick, waking up the target vCPU from its wait queue. Sometime later on the target where vCPU0 was running, it returns from schedule, where it previously scheduled itself out because it was on the wait queue, and then it resumes execution. And it wakes up in the IPI interrupt handler. So this process of sending an IPI and then the halted CPU coming out of it is entirely implemented in hardware when you're running on bare metal. And unlike the APIC timer, the entire length of the VM exit is not on the critical path, so we can't just time how long each VM exit takes to figure out what the overhead is. But we can do the same thing on real hardware and compare the performance. So I wrote a micro benchmark using KVM unit tests, where you have one vCPU execute halt, and then some short delay later, another vCPU reads its timestamp counter, sends an IPI to the target CPU, and then the CPU that was halted, vCPU0, in the first instruction of its IPI interrupt handler, reads the TSC again. And then that lets you know the latency from the start of the IPI to coming out of the halt. So back on that diagram before, we read the TSC right before writing to the APIC interrupt command register, and then right when we come out of halt on the far side. Read TSC, if you haven't heard of it, is a cycle-accurate counter in x86 that you can read. So the performance of KVM versus Sandy Bridge, it's about 12 times slower in the median case. I witnessed one case that was 400 times slower. But in real terms, it's about 5.5 microseconds to go from sending the IPI to coming out of halt, whereas on real hardware, it's half of a microsecond. And you get similar performance on more modern hardware. I don't have the bare metal performance, but the KVM performance is about the same. 5.5 microseconds on Ivy Bridge and about 5 microseconds on Haswell. So this benchmark is not using the floating point unit. So that's usually a good candidate for what's slow about switching to and from CPUs, but it's not being used here. The host is pretty much idle while this benchmark is running. So the virtual CPU, when it's coming out of its wait queue, is not contending for CPU time with other threads. And host power management is disabled, so they're not going into an extremely deep sleep state and then taking many microseconds to come out of it. So one of these steps is slow, but we don't actually know which. So we can throw more read TSC at the problem and measure each step. So delivering the IPI is pretty quick. The hardware transition is just 400 cycles, and then getting to the place where you wake up the target vCPU is just another couple hundred cycles. The really slow part is waking up the target vCPU from its wait queue. So that takes about, at a minimum, 7,300 cycles or 8,500 cycles in the median case. And then getting the CPU to run again is pretty quick, but also slow at around 3,000 cycles. So this isn't too surprising. Scheduling is often slow. Context switching is often slow. But it's slow even in the completely uncontended and completely cache-hot case. So there's no other threads that are scheduling on this virtual CPU's physical CPU that's blowing out the entire cache, and then it has to cache everything in. So imagine it would be even slower if you are running other threads on this physical CPU. So we can run an experiment where when we halt, instead of putting ourselves on a wait queue, scheduling ourselves out, if we just pull for that interprocessor interrupt, what's the performance of that? pretty good. So we started at about 5.5 microseconds before when we were scheduling ourselves out, and now it's about 1.7 microseconds when we don't schedule. Still about a microsecond slower than bare metal, but not too bad. And similar performance on more modern hardware. If you look at the per section cost of each after you eliminate scheduling, pretty obviously the cost of sending the kick to the target CPU goes from a lot to very little. The returning from schedule to getting the vCPU to run again also gets faster, and then the hardware transition also gets a little faster. So we can eliminate almost all of the latency by just not scheduling. So we should just never schedule, right? But scheduling is actually very often the right thing to do, and it's often the right thing to do from a performance standpoint. Because imagine your virtual CPU is halting because it's waiting for a network packet, and your network I/O thread is not being able to run because your virtual CPU is polling for the network packet to come in. So in that case, it's to your benefit to schedule. So it can improve performance, scheduling can improve performance, but scheduling can harm performance as well, as we've seen. So we can find a middle ground, which is halt polling. So imagine when you halt, for a short period of time, you poll for the interrupt, as long as there's no one else that needs to schedule on your physical CPU. And if the interrupt is delivered, you return and you get your quick performance of not scheduling. If the interrupt doesn't arrive, you've wasted a small amount of CPU and you still schedule yourself out. So the pros of this, it works on short halts, which is where the performance actually matters. If you have a 10 millisecond long halt, you don't really care about a 5 microsecond gain from coming out of that halt. And you continue to not block the progress of your other threads. So that case where your virtual CPU is blocked on your network thread running, this approach would still continue to not block that network thread from running. The downside is you have a slight increase in CPU usage. So if you have an idle VM that's just halting because it has nothing to do, meaning it's halting for no reason and polling is not the right thing to do, you get about a 1% CPU overhead. But if you care about turbo, this doesn't actually affect the turbo bins, of course, that are doing real work. So how does halt polling do? It improves your memcache round-trip latency by 1.5x. When the Windows event objects wait signal primitive about half of latency. And you can see we eliminated about 10 to 15 microseconds from our loopback TCP/RR latency. The remaining performance gap comes from still continuing to write to the APIC timer. There's still that 1.5 microsecond overhead from delivering the IPI to the halted CPU coming up. So actually, if you were to run your guest with idle equals poll, so it just never halts, and you ran your guest with no hertz off, you would actually get that blue line there as your virtual performance. But you don't want to do those things for many reasons. So the best part about halt polling is you can already play with it. Paolo already wrote the patch, and it's been merged into the 4.0 kernel, I believe. The way you use it is you set the halt poll nanoseconds KVM module parameter, and currently it defaults to off, so you have to explicitly turn it on if you want to use it. And there's further improvements that we can make. One that's very simple is to just turn polling on and off as it's needed. So if you notice that CPUs are halting and polling is always failing, just turn polling off. And then if you notice you start getting a lot of short halts again, turn it back on. And that will easily eliminate the 1% overhead that I mentioned earlier. Slightly harder improvement, but maybe possible, is automatically setting how long to halt and varying it based on the workload. I think this is an open question at the moment, so if people have ideas, post them to the mailing list. And then The last improvement is called lazy context switching, which was introduced a few years ago, also in a message passing talk. And this is the halt polling for any component of the kernel to use, not just KVM. So, so that's about it. Message passing is slow. It requires virtualization because it requires virtualizing halts, interprocessor interrupts, and for a no-hertz Linux guest, the APIC timer. We can save about 10 to 15 microseconds on round-trip latency by using halt polling. And the remaining latency is, as I said, those 4 writes to the APIC timer. They add about 3 to 5 microseconds. Sending the IPI still causes a VM exit and has to be virtualized. And then there's still about 1.5 microseconds from the halt wake up. And then so for round trip, it's about 3 microseconds. Okay, that's all I have for slides. Does anybody have any questions?
Just a comment. Probably if you use a deadline TSC timer, maybe you can reduce the number of VM exit.
The TSC deadline timer, same story as APIC timer. It's still an MSR write, still causes an exit.
Okay, so I'm wondering why you need to, write to the MSR twice.
Yeah.
So
yeah.
I think it should be done just the one write, but
I agree.
If you use a deadline kind of thing.
Yeah. So
the other thing is IPI. If you use posted interrupt, then probably you can avoid a VM exit.
The problem with posted interrupts in this case is there's no virtualized list halt. So the vCPU isn't running when you're delivering the interrupt. So posted interrupts doesn't give you any benefit.
Yeah, if it's not running, okay.
Yeah. In the back?
Have you looked at using config no hertz full as opposed to just no hertz? The no hertz just goes tickless on idle. No hertz full goes tickless if you have only one process to run. So if there's nothing contending with KVM, then it should already be in set a timer mode, and you don't have to reset that when you go idle, which would eliminate
Yeah,
that
sounds like it would eliminate the APIC timers. Yeah. Cool. Thank you.
In your description of the TCP/R test, you just described a single server and client, but you've got more than 2 vCPUs. I'm not sure how. Are you actually doing a ping pong around multiple processes there, or?
Yeah. So the idea with going for more CPUs, there's only 2 threads running, so it shouldn't matter, right? And it doesn't matter. The sort of variation is just noise. Could have left it at 2.
Okay.
Yeah. But
have you done tests?
The case where it might matter is if 2 CPUs are running on 2 hyperthreads, and then if you have more CPUs that are able to run on now 2 separate physical cores, the performance may get better.
Right. Have you done any timings with really more than two threads? So if you pass the token around multiple processes, for example.
Yeah. So not with TCP/RR, but with the Windows event objects, ran a workload in a Windows guest, and it got 40% improvement with halt polling. And that was a 8 CPU, I don't know how many threads, but all the CPUs were utilized during that test. Okay, thank you very much.